Welcome to 4.0 Cyber Defense. I am Dr. Al-Maliki. Today we examine the mechanics of defending data as it moves across inherently vulnerable networks. In a system context, data takes many forms. It operates as structured databases or in unstructured formats like emails and multimedia files. Network traffic is the necessary carrier vehicle for this data. It flows inbound to our systems, outbound to others, or laterally across internal nodes. Look at this visualization of network packets in transit. We routinely monitor this traffic for performance using tools like Wireshark. But the ability to monitor packets means plain text data is continuously exposed to interception. Networks are designed to pass information efficiently, not to protect it. Without mathematical intervention, data in transit is completely unprotected by default. We defend this exposed data using cryptography. This mechanism renders data unreadable to unauthorized users. Cryptography guarantees three pillars of security: confidentiality, integrity, and authenticity. Early methods used symmetric encryption, such as DES. Symmetric systems rely on a single shared key for both encrypting and decrypting the data. This creates a severe logistical flaw over public networks. Securely sharing that single key without it being intercepted in transit is practically impossible. Asymmetric encryption, specifically the RSA algorithm, provides the solution. It utilizes a paired, mathematically linked public key and private key. Asymmetric cryptography solves the secure communication problem by separating the key used for encryption from the key required for decryption. RSA secures data by leveraging the mathematical difficulty of factoring extremely large numbers. On this digital whiteboard, we begin the key generation process by defining two prime numbers, p equals 11 and q equals 13. We multiply these primes to establish n, our modulus, which equals 143. This is a public parameter used in the final encryption. Next, we calculate Euler's totient function, represented by phi. This is an essential secret value used to determine the keys. By subtracting 1 from each prime and multiplying them, 10 times 12, we reveal a totient of 120. This secret totient value establishes the mathematical boundaries required to generate the public and private keys. This display outlines two strict mathematical conditions for choosing our public exponent, e. It must be between 1 and the totient of 120, and it must share no common divisors with 120 other than 1. Multiple numbers satisfy these criteria, providing a pool of potential public keys. For this system, we select 11 to serve as the public key. We must now find the private key, d, which is the modular multiplicative inverse of e with respect to the totient. The entire security architecture of RSA relies on the fact that only someone who knows the secret totient can calculate this specific private key. This sequence demonstrates method 1, trial and error. We sequentially multiply 11 by increasing integers and check the remainder against 120. While trial and error eventually finds that d equals 11, it is computationally unviable for the massive cryptographic primes used in real-world security. Method 2 involves adding multiples of the modulus to 1 and dividing by e until a whole number is achieved. While slightly faster for human calculations, this method still requires iterations and fails to scale efficiently in computer science applications. Securing global network traffic requires a deterministic, highly scalable algorithm rather than iterative guessing. This two-column matrix illustrates the extended Euclidean algorithm, the definitive computer science solution for finding d. We execute the forward phase of the algorithm, determining the greatest common divisor of 120 and 11 to extract the remainders. Tracking the division steps down until the remainder reaches 0 confirms the greatest common divisor is 1, found in the second-to-last step. We begin the backward substitution phase, isolating that remainder of 1. We substitute the earlier remainder expression back into the equation, carefully maintaining the multiples of 120 and 11. Resolving the algebra reveals our coefficients, s equals -1 and t equals 11. The coefficient t provides our private key, d, demonstrating how modular arithmetic satisfies the requirements for asymmetric security. This visual represents node transmission. For our live encryption scenario, we have a plain text message of 7, a public key of 11, and our modulus of 143. The encryption calculation raises the message to the power of the public key, modulo 143. The readable number 7 is transformed into the unreadable ciphertext of 106. This ciphertext can now cross the network safely, immune to interception by network monitors like Wireshark. At the receiving node, a decryption process applies the private key, 11, to the ciphertext. Raising the ciphertext to the power of the private key, modulo 143, perfectly restores the original message of 7. The asymmetric mathematical loop is closed, successfully guaranteeing data confidentiality in transit. Data flows as inherently vulnerable network traffic, making cryptography non-negotiable for system operations. However, there are architectural trade-offs. While RSA solves key distribution, it requires much larger keys and significantly higher computational overhead compared to symmetric systems like DES. Because of this, modern security architectures like SSL and TLS protocols used for online banking rely on a hybrid model. They use RSA to exchange keys securely and symmetric encryption for the bulk data transfer. Cryptography provides the security architecture necessary for all modern digital operations.